Hello and welcome to today's lecture. Today we'll be continuing from the Otto cycle and we'll be introducing diesel cycle. So the diesel cycle is the ideal cycle for compression ignition reciprocating engines. And these engines are very similar to the uh, spark ignition engines. The only different part of it is the method of ignition. So like we've established in spark ignition, we have the spark plugs to initiate the ignition of the fuel mixture, while in the compression ignition engines, we compress the gas, the air and the fuel mixture until we go above the auto ignition temperature of the fuel and air mixture to allow the fuel to auto ignite by itself. Okay, so that's the major difference between. So therefore, the spark plug and the carburetor are replaced by fuel injection and in a diesel system. So the higher temperature results because of the higher compression ratio that carries the compression step to a higher pressure. So on the Otto cycle, we have the PV diagram shown here, and we can see that the pressure increase starts from stage 1 to 3 as it drops back. But in a diesel cycle, we have a, an isentropic process of pressure increase from stage 1 to 2. Then we have an isobaric process. Okay, the heat is added at a constant pressure. Then after that occurs, then there is a drop in pressure, isentropic drop in pressure to stage 4, and we have an isochoric, a constant volume heat removal. So the major difference is as a result of the different uh, heat addition process. Okay, in spark ignition, the heat is added to the fuel air mixture as by the spark plug, which initiates the explosion. But in the diesel system, there is a constant compression that occurs at a constant pressure to allow the auto ignition process to occur. Okay. So in the diesel engine, only air is compressed while the during the compression stroke. So eliminating the possibility of auto ignition. Therefore, diesel engines can be designed to operate at a much higher compression ratio, typically between 12 to 24. So like we said, the air is compressed as the fuel is injected, it automatically reaches its when it comes to the is injected into the compressed air, it will automatically uh, ignite because the compression within this region is already above its auto ignition temperature. So as it goes in, it auto ignites. So the fuel injection process in the diesel engine starts when the piston approaches the TDC, okay, and continues during the first part of the power stroke. So like we said, the fuel injection happens when the compression is at the TDC, the top dead center. So meaning that the air within the system is already compressed enough, and as the fuel is injected, it comes into the system which is under constant pressure, and that constant pressure is already above the auto ignition pressure for the auto ignition conditions for the fuel, and that leads to the fuel combusting immediately. Okay. So in processes 2 to 3, this is the heat addition process, okay, which we've already explained. And in fact, this is the only process where the auto and the diesel engine are totally different, the heat addition process, as you can see in their PV diagrams. So the remaining three processes, which is here, there, and there, are identical for both the ideal cycles. Okay. So the air is compressed adiabatically and reversibly here from 1 to 3, from 1 to 2. Then from 2 to 3, the constant pressure that raises the temperature to the value resulting from the combustion of the actual diesel. Okay, then the air is expanded at the vertical and reversible onto stage 4, and the air is cooled at constant volume to its initial state at 1. Okay, so this is used to define the air standard diesel cycle. So the thermal efficiency will look like this. So the net work divided by the total heat added to the system. This could also be expanded as the heat in minus the heat out divided by the heat in. And if we do heat in divided by heat in minus heat out divided by heat in, and we get this. So this will cancel out and we have 1 minus heat out over heat in. Okay. So like we've already established, in steam power plants and refrigeration cycle, we can use the first law of thermodynamics, but in diesel cycle, that is a non-flow system, and because of that, the changes in the heat and the work done by the system is affected by the internal energy, the change in internal energy of the working fluid. Okay. So with that, we can break down the processes. So between stages 2 to 3, at constant pressure, then the total heat in minus the heat out is equal to the heat added between stages 2 and 3 minus the work done at stages 2 and 3. And this is equal to the change in the internal energy. So therefore, the heat in is equal to the work out plus the change in internal energy. Okay. So if we know the values for the pressure at stage 2 and we know the values of the volume at stage 2 and 3, which is if we trace it here, sorry about that. If we trace this line here, that will be the volume at stage 2, and if we trace this line here, that will be the volume at stage 3. If we know those figures, then we also know the physical properties, obviously at constant pressure. But if we know the specific volume at this stage and that stage, we can use that to find the corresponding uh, internal energies at these 2 points. Then the summation of that to this will give us the total heat added to the system, or the total heat added to the system will be the CP, the specific heat capacity at pressure, at the constant pressure, times the change in temperature between stage 3 and 2. Okay, and the values are given here. So for the air, when the air is cooled between stages 4 to 1, when the heat is removed from the air, then the heat removed from the air is equal to the heat, the change in internal energy between stages 4 and 1. So with that, we know that there is a constant, volume operation. Okay, it's an isochoric operation. So the change in internal energy from, if we know the values for the change in internal energy at stage 4 and 1, then we can use that to solve it. Or if we know the temperature at stage 4 and 1, then we can multiply that to the specific heat capacity with respect to volume. Okay, and then note the difference with respect to volume. Okay, so with that established, then we can do the go back to the thermal efficiency, and we can replace the Q out and Q in with the formulas for expanded formulas with temperatures and the specific heat capacity. Now, like we already know that Cp, the specific heat capacity with respect to pressure, divided by the specific heat capacity with respect to the volume, will give you the value for the gamma. Now, the inverse of the gamma, which will now be the inverse of that expression, will give us Cv over Cp. Okay, and this will give us the inverse of gamma. So if we plug that in, if we replace this with gamma, so meaning that if we know the value for gamma, then if we don't know the value for Cv and Cp, and we know the value for gamma, then we can use that to calculate this equation. Okay. So we can even go to the extent of using the cutoff ratio. And the cutoff ratio is the ratio of the cylinder volume after and before the combustion process, just like the compression ratio for for uh, for spark ignition engines. Okay, and the cutoff ratio is given as the volume at point 3 divided by the volume at point 2. Okay, and if we account for this in that equation, okay, in this equation, then we can write it in this form. So the for the thermal efficiency for the diesel air standard diesel cycle, we can rewrite its equation in form of this. So if we know the value for the cutoff ratio and we know the gamma, okay, and we can use that to solve for the efficiency. Okay, so this brings us to the Brayton cycle. So the Brayton cycle is the ideal cycle for gas turbine engines. So it is used for gas turbines only where both the compression and expansion process take place in a rotating machinery. As you can see here, the rotating machinery here. So the compression and the expansion work occurs here. So this is where the cycle is used, the Brayton cycle. Now the gas turbine is more efficient than the reciprocating engine, primarily because the friction between the reciprocating piston and the cylinder and because of the fluid friction generated by action of the valves. The gas turbine engine, the gas turbine combines in one unit the advantage of internal combustion and the advantage of turbine. Okay, so the combustion engine will always have a combustion here and expansion to return back to the process. But in this case, the gas turbine engine will combine this combustion chamber, which is reminiscent of internal combustion engine, and the exhaust from the combustion chamber is used to move the turbine. Okay, and and that is how it takes advantage of the two process. So the gas turbine usually operates in an open cycle, and as you can see, fresh air is allowed to go into the system and the exhaust gases are allowed to leave the system. So uh, the resulting high temperature gases then enters the turbine at stage 3, where it's expanded and atmospheric pressure thus producing power, and the exhaust gases are allowed to leave the system and not recirculated back. Obviously, the composition of the gases, the exhaust gas is totally different due to the combustion process, but the inlet gas is always fresh air. So that's the one of the reasons why you will not recycle the exhaust gas. Okay. So the open gas turbine cycle described can be modeled as a closed cycle by utilizing the air standard assumptions like we've used in the previous slides. So if we use those assumptions, then the compression and the expansion process will remain the same. So these two will remain the same. So this means that the combustion process is replaced with a heat addition process from an external source, and the exhaust process is replaced by a constant pressure heat rejection, okay, process to the ambient air. Okay, and with that we can produce a PV diagram that accounts for this process. So we will have a stage 1 here. At a low pressure there is a compression, okay, a compression to a high pressure to stage 2, and from stage 2 heat is added to the system at constant pressure, and getting to stage 3, and there is an expansion, okay, and this expansion process that happens in the turbine that reduces the pressure to stage 4, and from stage 4 to stage 1 the heat that will be removed, the remaining heat will be removed from the system as it returns to its original state at 1, and it's also an isobaric process. Okay, so in this case we have mainly two isobaric processes and two isentropic processes. So in stage 1, as we know, air is compressed adiabatically and reversibly from 1 to 2, And from 2 to 3, a constant pressure isobaric heat addition to the air. Okay. Then there is an adiabatic and reversible expansion work done by the turbine from 3 to 4, and constant pressure isobaric heat loss from the system, heat removal from the system between stage 4 to 1. Okay, if we rewrite this, if we redraw it in on a TS diagram, temperature entropy diagram, we will know that stages 1 to 2 we have equal entropy, as we know. Compressor and turbine work will always give you an isentropic and adiabatic reversible process. Okay, so the thermal efficiency of air standard cycle, Brayton cycle, will be given as the network divided by the total heat added. And as we know, if we expand it, we have something like this: 1 minus Q out minus Q in. Now, if we, for a steam power cycle, as we know, we can use the first law of thermodynamics, but in this case, on a Brayton cycle, we can consider it as a steady flow system, and therefore the changes in the heat added and the work done is equal to the change in enthalpy. So with that identified, then the heat added to the system or absorbed by the process between stages 2 to 3 is given as the Q in equal Q23 equal to change in enthalpy between stage 2 and 3, and that could be rewritten as H3 minus H2, or if we know because it's a constant pressure operation, if we know the temperature at stage 3 and temperature at stage 2, then we can use the specific heat capacity to multiply through to get the same value. Okay. Then the heat removal between stage 4 and 1 is given as the Q out equal to Q41 equal to change in enthalpy between stage 4 and 1, and this it could be opened up to give us enthalpy at stage 4 minus enthalpy at stage 1, and this can also be solved by if we know the temperature at stage 4 and temperature at stage 1, and because it's a constant pressure, if we know the specific heat capacity with respect to pressure at this stage, at this particular pressure, then we can use that to multiply out to get the same value for the total heat added to removed from the system. And with that known, then we can rewrite this equation for the thermal efficiency for the Brayton, for the Air-Standard Brayton cycle. So we can do this for pressure ratio. So the pressure ratio is the pressure after and before the compression process. Okay, the pressure before the compression process and after the compression process, and this is given as P2 over P1, or which is also equal to P3 over P4. Okay, so if we are to replace this pressure ratio in the thermal efficiency, then we can write the thermal efficiency in this format. Now, for you students, you can try to prove this yourself. Okay, try to prove that this could be used in place of this. Okay, so you can use this as a starting point, or you can even go to the extent of yeah, start from here. I will suggest you start from here. Try to replace this with that. Okay, in this case, as you know that P2 over P1 is Rp and P3 over P4 is also equal to Rp. Now you can go way back with the relationship between P2, P1 and temperature, the relationship between temperature, pressure, and volume. If you can go back to that, but in this case, try to relate it so that you can have an expression that would not have volume in it. So, and that expression will be only for temperature and pressure, if you remember when we did it initially. Okay, so the pressure ratio, as we know, will affect the performance of a Air-Standard Brayton cycle. But how does it do it? So increasing the pressure ratio will increase the efficiency of the engine, and this will increase the work produced per unit quantity of fuel. And as we can see, the pressure ratio, as it increases from 5 to 20, then we can see the increase in the thermal efficiency of the Brayton Air-Standard Brayton cycle. And we can see the thermal efficiency rising from 35% up to about 63%, okay, in efficiency. So the gas turbine power plant. So we know that the higher the temperature of the combustion gases entering the turbine at T3, then the higher the efficiency of the unit. So that is, the greater the work produced per unit of the fuel burned. So the limiting temperature is determined by the strength of the metal turbine blades, and is much lower than the theoretical flame temperature of the fuel. So sufficient excess air must be supplied to keep the combustion temperature at a safe level. So we now introduce the jet engines. So in the power cycles considered up to this point, the high temperature, high pressure gas has been expanded in the turbine, such as the steam power plant and the gas turbine, or in the cylinder of a reciprocating auto or diesel engine. In either cases, the power becomes available through a rotating shaft. There is another device for expanding the hot gas, which is a nozzle. Okay? And this nozzle could be used to increase the velocity of a fluid at the expense of pressure. So therefore, if a fluid comes in at the wider entry of the nozzle, and as it goes out at the smaller end of the nozzle, then there is a kind of a reduction in the size, and with that you can increase the pressure, you can increase the velocity of the fluid coming in at stage 1. And now if we flip the nozzle on the other side, it could become a diffuser. Okay, and the diffuser is a device that does the opposite the work a nozzle does. So in a nozzle, the power is available as kinetic energy in the jet of exhaust gases leaving the nozzle. So in the entire power plant, consisting of a compression device and a combustion chamber, as well as a nozzle, is known as jet engine. So in this case, you can see the compression devices here, okay, and you can see the combustion chamber around this area with a full injector here, and you can see the turbine. Okay, the turbine is the blades that will be spinning, and you see the nozzle section and the exhaust. So since the kinetic energy of the exhaust gases is directly available for propelling the engine and its attachments, jet engines are most commonly used to power aircrafts. So there are several types of jet propulsion engines based on different ways of accomplishing the compression and the expansion. Compression here, okay, and the expansion at this stage. So since the air striking the engine has kinetic energy with respect to the engine, its pressure may be increased in the diffuser. Okay, so this is an example of an Airbus engine. Okay, Airbus A380. So this is a jet engine attached, two of them attached to the wing of this particular aircraft. Okay, so and this also shows us another a cutout view of the internal components of a jet engine for a powered USAF F-22 Super Cruise. So, the turbojet engine illustrated in the figure takes advantage of a diffuser to reduce the work of compression. So the axial flow compressor completes the job of compression, and then the fuel is injected. Okay, the fuel is injected and burned in the combustion chamber. So the hot combustion product gases first passes through the turbine here, where the expansion provides just enough power to drive the compressors, and the remainder of the expansion to the exhaust pressure is accomplished by the nozzle. So here, the velocity of the gases with respect to the engine is increased to a level above that of the entering air. So the increase in the velocity provides a thrust on the engine in the forward direction, and that's how the jet moves forward. Okay, and if the compression and expansion processes are adiabatic and reversible, the turbojet engine cycle is identical to the ideal gas turbine power plant cycle, and the only differences will be the physical. It will be the compression and the expansion steps that carries out in the device of different types. Okay, so for rocket engines, what are the major differences between the rocket engines and the jet engines and the other equipments that we've discussed so far? The rocket engine differs from the jet engine in that the oxidizing agent is carried with the engine. So instead of depending on the surrounding air for burning the fuel, the rocket itself is self-contained, meaning that the oxidizer is carried along with the fuel. So this means that the rocket operates in vacuum, obviously, such as in space, and obviously when it has left the atmosphere. So the performance is better in vacuum because none of the thrust is required to overcome friction forces that could have been exerted on it while still within the Earth's atmosphere. Okay. So in rockets burning liquid fuels, uh, the oxidizing agent is usually liquid oxygen. So this is pumped in from the tank into the combustion chamber, and simultaneously the fuel normally used is kerosene is pumped into the chamber and burned. The combustion takes place at a constant high pressure and produces high temperature product gases that are expanded in a nozzle. So the rocket burning solid fuels, the fuel which is usually organic polymers, and the oxidizers example are ammonium perchlorate, are contained together in a solid matrix and stored at the forward end of the combustion chamber. In an ideal rocket, the combustion and the expansion steps are the same as those for an ideal jet engine. A solid fuel rocket requires no compression work, and in a liquid fuel rocket, the compression energy is small since the oxidizer are pumped as liquid. So this will be the end of this session for gas power cycles. And there are a couple of tutorials, and I will hope with this information and maybe with your further studies, personal studies, okay, you'll be able to solve most of the tutorial questions and get a clear understanding of how this is applied in real life scenario. Okay, and that will be it for this on the gas power cycles. See you guys on the next lecture. Bye for now.